Think of AI as a factory, handling both simple and complex tasks. Basic jobs may run fine on CPUs, but the advanced ones, like the advanced AI techniques like neural networks, they need heavy-duty power of GPUs and TPUs. But it's not just about the hardware. These systems also need high-performance network to keep data flowing smoothly. Without the right network design and techniques, even the most powerful machines can stall. The key to success is balancing computing power with a robust network to keep everything running efficiently. And this is what we're going to learn here today. When we talk about AI, there are a bunch of cool techniques that we're going to be running in your AI data center. And these, if we name a bunch of them, things like clustering or maybe training or inferencing, these AI techniques require heavy lifters. They require special hardware devices and hardware parts in order for your AI operation to run smooth and efficient. So things like CPUs, that's not going to cut it. You need some special kind of hardware such as GPUs and TPUs. We've already established that. But hey, is it just about those hardware? No, it's not just about a bunch of cool GPUs working together. The fact is, you're going to need hundreds or even thousands of these GPUs scattered across multiple compute nodes. And this is where it gets even more challenging when you have those different GPUs scattered everywhere. You're going to have to form clusters. Who's going to make those GPUs communicate between those different cluster nodes? Well, you got it. The network. You need to create a well-designed network. When I say well-designed, there are lots of specifications and topologies and architectures that you need to follow in order to make sure that this is a well-designed network. So when you create that network, you're going to make sure that there is some kind of a ratio between the GPUs that you have scattered across the different clusters or maybe in a single compute node and the NIC cards. How many NIC cards do you have? Well, it's going to be some kind of 1-to-1 ratio, 1 GPU to 1 NIC card, or maybe 1 or 2-to-1, 2 GPUs to 1 NIC card. Why? Because this is the sweet spot for efficient AI data processing. Is that it? No, that's not it. You also need to make sure that you have a rigid design that will enable communication, data communication to happen between those different GPUs in a single cluster across multiple clusters with zero packet loss, lossless fabric. So how's that going to even work? We all know that the most important couple of processes in AI model is training and inferencing. When it comes to training, this is the heavy-duty part of AI. It requires major power, both in terms of storage and networking, because you've got massive continuous data streams moving at top speed. The challenge here is that the traffic can be bursty, yet predictable, which means that you need some kind of quality of service or congestion management techniques to keep everything on track. The crucial point is that even if one data stream hits a slowdown, it can hold up the entire process. Now, if there is high latency or packet loss during training, that's where things can really go sideways. When data get lost, it has to be retransmitted, which can cause significant delays. This is why a non-blocking network is absolutely essential for keeping everything flowing smoothly without interruptions. Unlike training, which is usually done in big data centers, inference often happens on the go, whether it's on smartphones, self-driving cars, or other edge devices. So these models are deployed closer to the user, like at mobile towers or remote data centers, to minimize delay. And what's the most important factor here? Low latency. Even though inference does not demand as much raw power as training, it still needs to be fast and reliable. Too much jitter, those small, teeny, unpredictable delays, can mess up data loading during training or cause lag in real-time responses. That's why it's crucial to have a network that ensures consistent, low latency and minimal jitter. So let's take a look at this diagram, which breaks down the AI machine learning application lifecycle and deployment model, giving you a clear view of what's needed at each stage of the process. Models are trained at the data center first, then deployment happens on the edges. After which, you may receive an inferencing request at the edge AI inference engine. If the AI stumbles on a problem, the troublesome data is commonly uploaded or sent back to the data center where original trained AI model resides for further training of the original AI model, which at some point replaces the inference engine at the edges. AI and machine learning are growing in incredible rate, and they're doubling in size every few months. As they get more powerful, they need more data and longer training cycles, which leads to a big increase in server-to-server communication. Well, where are you taking us? Well, you need to handle all of this. And data centers use some kind of topology which will really tolerate this expansion. This is the spine and leaf architecture, which is often called the Clos topology. In this topology or the setup, we typically see a two-tier design, two-tier network where leaf switches connect to servers and spine switches connect to the leaves. The brilliance of this design is that any server, is just 3 hops away. This is standard, 3 hops away all the time from the other server, making communication super fast and efficient. Hop 1, as you can see here, is from the source server to the first leaf. Then the second hop is a tunnel across this spine all the way to the far end leaf. And then finally, the third hop is from the leaf, the destination leaf, to the destination server. Need more servers? No sweat. Just add a leaf switch. You need more bandwidth? Add more leaves. The beauty of this design is that every leaf connects to every spine, and you just need to make sure that those spines have enough pores to handle the new connections. And here's the best part. If you need more bandwidth, forget about ripping out cables. Nobody wants that headache. Instead, just toss in more spine switches and hook them up to the leaves. As your network grows, which is a good thing, so does the chance of failure. Good news here is the bigger the network, the less impact a single failure has. In a 4-spine fabric, as you see here, losing 1 spine means what? Losing 25% of your bandwidth, which is maybe scary. But if you lose 1 spine in an 8-spine fabric, do the math, this is going to be 12.5%. So the equation is going to be more spines is equal to more resilience. And let's talk about leaves. If 1 leaf fails, that host connected to that specific leaf is going to lose 1 link, assuming that this host has some kind of dual link and it's dual homed to the, another leaf switch. So it's redundant. In another way, it stays connected just with reduced bandwidth until the issue is resolved. To keep your network rock solid, especially during real-time inferencing, building an, extra redundancy is the way to go. Adding more spine switches doesn't just increase your bandwidth, it makes your network resilient enough to handle multiple failures. So even if a few things go down, your system stays strong, keeping everything running like a well-oiled machine. Summary time. AI and machine learning hardware requires GPUs and TPUs and also distributed processing through a well-created network design. Scalability of that design includes a Clos architecture that allows easy expansion with leaves and spine switches. The expansion will give you redundancy. If you have more spines, then you get less failure impact. And if you have more leaves, then you get more port density. Whereas for efficiency, this is where you have 3-hop communication for smoother data delivery and load balancing. I hope that this was informative. I'd like to thank you for viewing.